Welcome to part one of position, velocity, acceleration, and accumulated change. So here we have a problem. A car is traveling at 88 feet per second when the driver applies the brakes to avoid hitting a dog that has run into the road. The distance the car has traveled from the point when the brakes were applied is represented by the function f of t equals 88t minus 8t squared feet, where t is measured in seconds and f of t is measured in feet. Based on this scenario, how long will it take the car to come to a stop? Okay, so the car is, we want to know when it stops. So the function that we're given, f of t equals 88t minus 8t squared, that's our position function. If we want to know when the car has stopped, this is when velocity equals 0. Right? It says stop has to do with how fast you're moving. If you're stopped, you're not moving. Your velocity is 0. Right? So we need to take the first derivative. Right? So we're going to differentiate our function here. F of t equals 88t minus 8t squared. Right? And if we take that derivative, we have f prime of t is equal to 88 minus, right? And then 2 times negative 8 gives us negative 16t. Right? So that is our velocity function. We'll just set that equal to 0. Right? So we have 0 equals 88 minus 16t. I'm going to add 16t to both sides, so 16t equals 88, and then divide both sides by 16. T is equal to, it's about 5 point something. 88 divided by 16, 5.5. Right, so 5.5 seconds. Right, so that's how long it'll take for the car to come to a stop. We want to know, in the next question, how far will the car have traveled before stopping? Well, traveled, that's our position function, right? That means what does our position change to, right? How much does our position change? All right, so we're going to use the function that we're given there, the 88t minus 8t squared, and we want to put in the time, t equals 5.5, right, because that's when we stopped. Right, so we're just going to evaluate our position function at 5.5. So we have 88 times 5.5 minus 8. I should have written this a little lower. I'm going to run right into the word position. 8 times 5.5 squared. Right? Right, so now calculator might be nice. Right, so that's 484 minus and times 8 there. So minus 242. Right, so that's going to travel, that's pretty easy subtraction there, 242 feet. Right, so f of 5.5 is 242 feet. That's how far our car travels. So how fast is the car traveling when the brakes are applied? When the brakes are applied, no time has gone by. So t equals 0 here. Right? So and I probably, before we move on to the next question, just for your notes, I think this is in your notes, I'm just going to, just to put a little reminder here of what we did in the last question, which was we evaluated position function. And that was for, oh, can I erase that much? I think if I change the eraser side, I'm going to get rid of the word position. There we go. So evaluate position function, and it was t equals 5.5. Right? All right, so moving on to the next one. How fast is the car traveling? When the brakes are applied, t equals 0. Fast is the velocity. So we want to evaluate the velocity function at t equals 0. All right, so we have our velocity function up in the first problem there in blue. All right, so we'll just substitute f prime of 0 equals 88 minus 16 times 0, and that's going to be 88 feet, right? So f prime of 0, I mean 88 feet per second, minute, second, 88 feet per second. 88 feet per second, right? That makes sense because it said it's traveling at 88 feet per second when the driver applies the brakes, right? So that makes perfect sense that our velocity would be 88 feet per second when t is 0. It says it right there in the question. But now we've shown mathematically that it was really true. How quickly is the speed at which the car is traveling? That is not a good sentence. How quickly is the speed at which the car is traveling decelerating? I think we have one too many is's in this sentence. Decelerating. All right, so that means this is we want to know about acceleration, right? So we need to find the acceleration function, which means we need to take the derivative of the velocity function, right? So d dx, trying to color code it so everything's in a different color. So I'm going to write in black. Oops, I still had the eraser in my hand. All right, so d dx. All right, and we're going to differentiate acceleration there. F prime of t equals 88 minus 16t. Take the derivative of a constant, that's 0. So the only thing that's going to be left is the negative 16 using our power rule. So f double prime of t is going to be negative 16. So this f double prime here, this is our acceleration. I'm going to move this over just a little bit so that I can also write in a of t. Right? That's acceleration. We differentiate it up here. Ooh, now I'm a little crowded. There we go. And then over here, this was velocity. So v of t is that. And no matter what time it is, we have a constant rate of deceleration here. So regardless of what t is, we have a constant rate of deceleration. It's decelerating because it's negative. It's slowing down. And that constant rate of deceleration is 16 feet per second, or 15 feet per second squared. If the dog were 232 feet away, at what speed will the car be traveling before hitting the dog? Assuming the car continues in the same path and the dog does not move out of the path of the oncoming car. All right, so we're looking at the speed the car is traveling. All right, speed is just velocity, but it's always positive. All right, so regardless of the sign, it would just be positive. All right, so let's look at the next page where I have some space for this problem. And I have it all solved out. So since the dog is 232 feet away, the car will hit the dog if the dog does not move out of the path of the oncoming car. But you know, dogs are really smart, and I think this dog, he's going to jump out of the way and be just fine. So don't worry. Dogs are smart. So the car travels 10 feet beyond where the dog is located. By setting the position function equal to 232, the time it takes the car to reach the dog can be determined. Substituting this value for time into the velocity function for t, the speed the car is traveling when the car reaches the dog can be determined. Right? So, and our speed is positive. Right? Because the car is moving in a positive direction. It's moving. It keeps on moving. All right. So here is our position function was 88t minus 8t squared. We want to know the speed when the cars travel 232 feet where the dog is, right? So we need to find out, first of all, how long it takes the car to get there. So we have 232 equals 88t minus 8t squared Move the 232t over. You can factor out the -8. They're all divisible by -8. Gives you t squared minus 11t plus 29 equals 0. That is not factorable. 29 is a prime number. 29 and 1 are its only factors. So we'll use the I use the quadratic formula. I don't think I need to have the work for the quadratic formula on here. I think you're okay, right? I of course threw out if there was a negative answer, I threw the negative out. Because time has to be positive, and I rounded. So t is approximately 4.4 seconds. Evaluating the velocity function at t equals 4.4 seconds, the velocity of the car can be found as it reaches the dog. The instantaneous velocity of the car at time t is the derivative of the position function with respect to time. All right, so v of t is just the derivative of 88t minus 8t squared, the position function. Right? And we know from the last page it was 88 minus 16t. We're just going to plug in 4.4 for t. And we find out that the car is traveling at 17.6 feet per second. It's pretty fast. Hopefully the dog has moved out of the way. But like I said, dogs are smart. I think he's okay. So only one of the three functions, position, velocity, or acceleration, is needed to find the other two. By integrating the velocity function, the position function can be found. By differentiating the velocity function, the acceleration function can be found. Taking the derivative of the position function gives the velocity function. Taking the second derivative of the position function gives the acceleration function. By knowing the acceleration function, integrating once gives the velocity function, and integrating twice gives the position function. For instance, the equation for velocity can be found using the acceleration function and integrating, using c as the constant of integration. By solving for c using a specific value for t and a corresponding value of the function, the specific velocity equation can be determined. So here I added something from the original question. Here we have the acceleration function. That was -16 dt. We know that the car was traveling 88 feet per second when the driver applies the brakes. All right, so here is a point that we have. So when t is 0, velocity was 88. So now we can integrate this. All right, so we integrate, use the power rule. All right, our exponent is going to increase by 1. And of course now there's no exponent there, it's to the 0 power. So that means it will be 16t. Right? And divided by 1 is still the same thing. All right, so this is our velocity function minus our constant. So we have v of t equals -16t plus c for our constant of integration. Right? This is an indefinite integral. We need to have the constant of integration. And now we're going to solve for c. Right? So we can plug in 0 for t and set the function equal to 88. Replace v of t with 88. So 88 equals -16, 0 plus c, and you can see that c is 88. All right, so that means our velocity function is v of t equals -16t plus 88. That's our velocity function. All right, now on the next page, we're going to integrate velocity and get acceleration. All right, so the equation for position can be found using the velocity function and integrating using c as the constant of integration. Then by solving for c using a specific value for t. You know, I typed a lot here, so I'm allowed 2 typos. There we go. For t, and for the value of the function, the specific velocity function, we can find the specific velocity equation. Got tongue-tied there. All right, so here I took something from the question. Initial position, the car has not traveled yet. All right, so, and when the car just applies the brakes, right, he hasn't gone anywhere yet. And then he travels. So we have 0, 0 as a point. So now we're going to integrate this. Right, so we have, again, we're using the power rule. So s of t equals, so we're going to increase the exponent by 1 and divide by the same thing, and then increase the exponent by 1. Now it's 88t to the first, and dividing by, and we don't even need to write the 1 there, and of course dividing by 1 gives us the same thing. And then of course our constant of integration. Put the eraser in the wrong spot. So let's reduce that. S of t equals negative 8t squared plus 88t plus c. And now we just plug in, set our function, replace s of t with 0. Okay, and we replace our t's with 0 as well. And we can see that c was 0, right? So 0 equals, or everything there is 0. All right, so our position function, s of t, is negative 8t squared plus 88. And remember, that was exactly what we had, oh, plus 88t. That was exactly what we had at the start of the question, right? So you can, if you have just one function, you can, and you have the acceleration, you can integrate to get the velocity and then integrate again to get position. And see, we got the exact same function again. All right, so it's easy to get the other functions so long as you know a single constraint and you know one of them. All right, so we want to know the total change in position for the first 5 seconds. All right, so that we're going to integrate our velocity function. Excuse me, I almost said position function. Our velocity function. Right? If you integrate velocity, you get change in position. So our velocity function, if we go back, oops, was, oh, I passed by it, didn't I? There it is, negative 16t plus 88. So we're going to integrate that. Right? And we want to know the first 5 seconds. So from 0 to 5, and then I need dt. All right, so total change in position. To get the total change, take the definite integral and evaluate. Right? And you're going to be integrating and evaluating the velocity function to find total change of position. If you wanted to find total change of velocity, you'd integrate the acceleration function. All right, and evaluate that one. All right, so let's integrate. All right, so we're going to have negative 16t squared divided by 2 plus 88t, and we're going to evaluate that from 0 to 5. And that reduces to negative 8t squared plus 88t, and from 0 to 5. So we have negative 8 times 5 squared plus 88 times 5, and then minus, I didn't give myself enough space. Well, this would be negative 8, 0 squared plus 88, 0, which is going to be 0. All right, so we only have this one here. All right, so this is going to be negative 8 times 5 squared. So negative 8 times 25 is going to be negative 200. Plus, and then 88 times 5 is going to give us 440. And that's just 0, which means 240 feet is the total change in position. Ooh. In the first 5 seconds. Right? And that's the end of this problem here. Thanks for watching, and stay tuned for more problems with position, velocity, acceleration, and accumulated change. Right? Bye for now.